Hello everyone, my name is Chase Morgan and today I will be presenting my midterm oral presentation for my capstone. So the project idea is to create a simple 8-bit computer from transistor to transistor logic chips. So there are a wide variety of these logic chips on the market that are very simple but do very useful functions. And when you combine the right ones together, you can actually make a fully functional computer. So the goal of this project is to create an educational tool for programmers and software engineers to learn from. And the reason being is because some programmers, when they go to school, uh, they might not take a computer architecture class or know how a computer works on the inside, like all of the internals. Um, this is a bad thing because it can lead to inefficient programming and the creation of slow and insecure code. If you think of the computer as a black box, a mysterious entity where you just input a program and you have results as an output, you're not going to truly understand how to be a good programmer and how to manage things such as threads and memory allocation. So, like I said, the main goal of this project is to serve as a learning tool for aspiring programmers slash computer scientists. So the computer isn't going to be necessarily fast or very performant, but it should allow people to learn. So just a brief materials list so far. I'm not going to go too into detail, but you can see that I've used a lot of 74LS series chips made by Texas Instrument, uh, and they create a wide variety of chips with many applications. And you can see here that every module uses LEDs, and the reason for this is we want to see the data that it goes into every single component of my computer, so you can use that to learn from. So let's just get into the project functional requirements. So the system should allow the user to input programs into the machine through a desktop or laptop. The reason I did this is because I want the computer to be simple and convenient to use, and through the use of modern technology, we can take a rather archaic design and make it easy to program, which originally would not be very easy to program at all. So we want that. We want the user to be able to create programs quickly, to learn faster. We should also the system should also allow the user to view the output of programs through a modern machine. This is very good for when you're presenting the computer. You could actually show the output on a smartboard or over a WebEx meeting or something like that. It should also allow the user to run programs stored in RAM. The reason being is because this is a pretty much basic requirement of all computers that use the von Neumann architecture. So both program data and variables need to be stored in the RAM. My computer should be able to perform mathematical operations such as addition and subtraction. You can implement other mathematical functions on the hardware level, but these are the only two ones that I'm doing because it's pretty much the bare minimum. And like I stated earlier, you do not need to have a very complex machine in order to learn from it. Additionally, the system shall allow programs to save and load variables to and from memory. This is basically another requirement for the von Neumann architecture, which is the architecture used in most modern computers. And this just allows for more complex programs. The system shall contain a CPU, RAM module, and I/O module. This is just another basic requirement, so we must state it. And then a not so basic requirements that I specifically need for the system is that the system shall allow the user to view the contents of every register and component at any given time during the program's execution or the machine cycle. This is to get a truly full understanding of the computer, because in order to understand data transfer and where bits of data are going to and from, you need to be able to see what's in the contents of any register. The system shall allow for conditional branching within the programs. This is not a strict requirement for computers. However, it allows for way more complex programs and way more useful programs. So that's why I want it in my computer. And along with that, the system shall calculate whether the accumulator register has a number 0 or a negative number in it at any given time. And this falls in hand with conditional branching, which we'll get into in a moment. So this is just a basic diagram of the I/O module for the computer. So we have a modern machine where you can use a graphical user interface to write your code, and then that'll be taken to a microcontroller, which will be then convert that code into digital signals or machine code that the 8-bit computer will store in RAM. Additionally, the program output, once the program is done computing, will be sent to the microcontroller and then sent back to the machine to present the information that has been calculated. So some non-functional requirements of the computer is that the clock module should run at a minimum speed of 0.13 hertz. This is extremely slow, but it's slow enough so that the computer can still run without the interruption of the user, and the user can still take in all the information that's going on. And it should allow a maximum speed of 3.6 hertz. So in a second, it takes about roughly 3 clock cycles. So it runs a little bit fast, but it's still not so fast that the program is completed basically instantaneously. So you can still see what's going on. So all mathematical operations will be performed on signed 8-bit integers with a maximum value of 127 and a minimum value of negative 128. I could have done unsigned to allow for bigger integers for addition. However, we would not be able to subtract, which is very important, so I had to make it signed. The RAM module should hold 16 8-bit numbers for a total of 128 bits of memory. 16 memory cells is because each instruction is 8 bits long, with 4 bits for the opcode and then 4 bits for the address, which gives us a total possible memory amount of 16. There should be 9 instructions, 2 for math operations, 2 for storage, and then 2 for jumping operations. And then you have some miscellaneous ones like the out, which is outputs the program results, the no op, which does nothing, and then the halt instruction, which halts the computer once execution is done. The control sequencer will produce a 15-bit word per clock cycle. This is to control every module with micro instructions, which we'll get to in a little bit, and then the entire computer must operate with a 5-volt power supply. This is so the computer can be portable and easily stored, and also you can power it with a USB port, which is good. And then all chips using the design must have simple operations. So I'm not going to take a microprocessor that's the size of my finger and use it in this project, because that would be too easy and it would ruin the purpose of this project by it abstracts away everything basically besides the RAM and the CPU, but we want to go deeper into the actual computer architecture. Just some current progress. We have the clock module. This is just a basic high-level view of how everything's going to be connected to each other. So we have the clock module that goes to every single component. This allows for synchronization of actions. And then we have the 8-bit wide bus, which almost every component is tied to. So every component can output its contents to the bus or input from the bus. And then we have the control sequencer, which controls the traffic of every component with the use of micro instructions, which is how we transfer data around through the control sequencer. And then we have the RAM here at the bottom, which is how we save our program and also data that we are using during execution. So the first diagram that I've created is the clock module diagram. So the main component that we use for it is the 555 timer chip, which is a very commonly used timer chip throughout a bunch of applications in electronics. And then I modified it. So we have an input from the user to either toggle manual mode or automatic mode. So in automatic mode, the clock pulse is outputted automatically, and then you can change the speed with this potentiometer right here. We also have a manual mode, so the user can pulse the clock signal themselves for them to study the machine and then go on to the next clock cycle. And then we also have the halt input right here, and this is directly controlled from the control sequencer. So whenever the program is done running, the control sequencer can halt the computer and stop it from running, because if it were to run on, it would affect things in RAM and corrupt data. So the next module that I completed was the basic register module. It utilizes a 74LS377 8-bit register. And we see here that we have both input and output tied to the same line, so just data 0 through 7. The input is from the bus, and also the output of the data is written to the bus. And we control that with an input line and an output line. And you can see here, this is unnecessary for all computers, but we use it for educational purposes. In this context, these are just LEDs that will constantly display the output of the register, and then that is sent behind these AND gates that we can use to enable it to go to the bus. We also have a clear line to clear the contents of the register. So the next thing I worked on was the instruction set for my computer, and just briefly, we have the no operation, which is when the computer does nothing, and then load and store, which loads the contents of the address X into the accumulator, or stores the contents of the accumulator into address X. This is how we do mathematical operations. Then out for outputting the accumulator register contents. And then we have add and sub, which takes a memory address and adds it to the accumulator or subtracts it based on which instruction you use, and stores it back into the accumulator. And then we have our conditional instructions right here for creating if/else statements and also loops. So if the accumulator contents is 0, then we jump to a certain address, or if it's negative, we jump to a certain address, depending on what type of instruction you use. And then we also have the halt instruction, as stated earlier, that will halt the execution of the program. So instructions are actually high-level abstractions that the computer doesn't understand, so we have to break it down into micro-instructions for the computer to perform these complex actions. So basically all micro-instructions do really is it allows the input or output of certain registers. And then we also have some different ones, like the program counter can input an address for jumping. It can enable itself to increment to the next address to load the instruction from. And then we have the subtract mode for subtracting, and then we also have RAM in and out. So I'm not going to go over these in detail, but this is just a brief view of all instructions broken down into a sequence of micro instructions. So this is every single possible function that the computer can perform, and from this we get very complex programs. The next thing I worked on was a circuit that I have designed called the instruction deconditionalizer, which takes in the input of the instruction and then the negative and positive flags, or the negative and 0 flags from the accumulator, and it will decode instructions into the true instructions that they should run. So this is how we do conditional branching in the program or in the computer. Most computers use state registers instead, but this is a purely combinational circuit, which makes it far more simpler and far more faster to complete conditional branching. So just an example of that, this instruction or this circuit actually only works on these two instructions. So if you call the jump Z instruction and the Z is 0, you actually, that instruction gets converted into the no op construction. But if jump Z is called and the zero flag is high, then you actually load that address into the program counter to actually jump. And the same thing for the negative instruction. So the next module I worked on was the B register for the ALU. You can see here that it's just a modified basic register. However, it only inputs from the bus, and the output immediately goes to the adder / subtractor. So the output of B will never be on the bus. And then the next one is a little bit more complex. It's the A register, or the accumulator register. We can see here that a couple differences are that the output always goes to the adder / subtractor. And right here on the right side, we see that we have a cascade of OR gates, which computes whether or not 0 is in the register. So if all of these are 0, then the final one will be 0, which gets inverted into a 1 and goes to the 0 flag. And then negative is just the last or the most significant bit of the data in the register, because if the most significant bit is 1, then we know it's negative because we're using signed arithmetic. And then lastly, for the ALU module, we have the adder / subtractor, which right here we can see that we have a bunch of OR gate or exclusive OR gates that if the subtract mode is enabled, it will invert all the bits, and then that goes to two 4-bit adders cascaded together, which will output right here. And then these two chips right here are just representative of the A register and the B register. And the principal component behind the ALU is the full adder, which just takes in 3 bits of information and it will add them together with a sum and a carry out. And you can actually cascade these together to get any large adder that you want, which is important to realize because a lot of computer science is very small inner workings that get abstracted away until you get very complex operations. So next up we have the program counter, which you take in data from the bus if you need a jump. But basically all that it does is if your program counter enable line is high, you will increment to the next address in order to reference that instruction from memory. We can also see here that it can output its contents to the bus and input. So the principal component behind the program counter is the JK flip-flop, which is a very useful circuit that has been used for decades. It can be used to half frequencies along with other applications, but in this case we're using it to count in binary. So you can see here that we can take the output of the first JK flip-flop and input it into the clock, and this will just half the frequency. So we see here that for the last output we have a lot of zeros and then ones, and then this one has half the zeros and then it goes to 1. So the frequency of change doubles as you go from left to right, which is how it, and you can see here it actually just counts in binary, starting from 0 and going to 15. And then we have the RAM module, which is one of the most complex parts of the computer. We have a 32K RAM chip right here, and the reason we use 32K is because there's no module on the market that has 16 by 8 words. You can see here we have the memory address register right here, and it constantly outputs its contents. And then you have the microcontroller, which is the interface between modern computers and the 8-bit computer, and it will write to the RAM module. It has 2 modes, program and run. So in program mode you will be able to write data to it, and then in run mode it will just run the program. So current trends in the industry, the AT Mega 328P is an example of an 8-bit microprocessor used in modern controllers. The main advantages of using 8-bit microprocessors today is because they are very simple to create, in contrast to like 32-bit or 16-bit microprocessors. So they're simpler, they're cheaper, and they also allow for less current leakage and can work in higher temperatures because of this. So they're used a lot in home projects and also specialized embedded applications such as medical technology and sensors for high temperature areas such as engines. So some potential difficulties with the project is the chips that I buy are usually from China. So if there's delays or chips are out of stock, then I will have to find and do more research to find different chips to use. Some chips don't exist for my required purposes. Such as a RAM chip, I had to find a too big RAM chip because the one I needed doesn't exist. The size of the computer when I actually build it has to be built not to a ridiculous size so I can bring it for demonstrations once it is physically built. And if too much current is drawn from the computer, I will need to use a bigger power supply. And then a small amount of RAM that we use, programs can only be so complex. So some future plans for this project. By the end of this semester, I want the whole computer should be fully designed and diagrammed. A complete bill of materials for the computer. All the code for the computer should be done for the input-output module, and then all parts should be purchased. For next semester, at the end of next semester, all module prototypes should be completed, and then final designs should be created, and then lastly, all modules should be integrated together to run the computer. And then here's some references for some images I used. Thank you.